Hello everyone. In this video I want to talk about the question how many quadrants a line segment or a line can intersect in the plane. So our question is, how many quadrants can a line intersect in a plane? So what do we mean with this question, and what is the motivation behind this question? The motivation behind this question is, let's say, for example, we want to do some kind of array casting. In array casting, we have to know how many quadrants we need to check in order to march the array in a certain direction. In a quad tree, which is basically a subdivision of a certain region in plane, it's a recursive subdivision, and then in each level subdivides a certain region into 4 quadrants, and we have to be able to identify those quadrants which line is going to intersect. Okay, that's the main question. So this turns out to be the question. The answer to this question, in general position, tends to be 3, and we have to find out the reason why this is 3. So, but first, before starting to consider any line in general position, let us consider some specific cases, some degenerate cases. Like, for example, this case, right? When the line passes through the origin, then all of the quadrants are being intersected, right? So we are not talking about this case. In another case, where the line is parallel to one of the axes, only 2 quadrants are being intersected, like in these cases, right? And we are not talking about this case either. So our case is, in its most general form, is like this. Okay? And as we can see in this picture, that the line crosses 1, 2, and 3 quadrants. Maybe we should just name them correctly. This is the quadrant 1, this is 2, 3, and 4. In this case, the line passes through the quadrants 2, 3, and 4. Now, if you look at this configuration, see that any point in this quadrant is in front of the line. What do we mean? The quadrant being in front of the line. If we take the normal vector of this line and select its direction to be such that the origin of the coordinate system is in front of the line, then we can see that all of the points in the quadrant 1 is essentially in front of this line. So what happens if we move this line around? Let's consider such a case. Let's say, for example, we have shifted the line such that, but we have to switch the orientation of the normal vector now. Now we see that this quadrant is not being intersected, but these first, second, and fourth quadrants are being intersected. In a similar manner, we can draw other lines, for example, like this. See that this is not being intersected. Draw another one like this, and select the normal vector to point towards the origin, and we see that this quadrant is not being intersected by the line. So what is the observation here? The observation is that when we select the normal to point towards the origin, then the quadrant in which n lies is not being intersected. In all these cases, you see this behavior consistently, right? Here, normal vector, in this first example, you see that the normal vector lies in the first quadrant, right? And this is exactly the quadrant which is not being intersected by this line. In the second example, the normal vector lies in this quadrant, in the third quadrant, and the third quadrant is not being intersected. In the third example, normal vector lies in the fourth quadrant, and it is not being intersected. And the fourth example, normal lies in the second quadrant, and the second quadrant is not being intersected. So let's see if we can somehow formulate this more generally. And if we can prove that this indeed is the case, then we can easily say that this is a general rule. Now let's consider a signed dot product function. Let's call it like this. And we call this line L in each case. X minus P dot N. So in this equation, in this formulation, X is any point on the line, and then we select any point on the line such that P dot N is not equal to 0. That is, which means that X dot N is not equal to P dot N. Okay? I'm sorry, this should be 0. X dot N does not equal to 0. Which means that the line should not pass through the origin, because as you can see from our very first example here, if the line passes through the origin, then that line will intersect all of the 4 quadrants, which we do not want to show anyway. So, how should we start now? As you can see, the equation of the line is x minus p dotted with n equals to 0. Now, what we did say, what was our assumption concerning the normal of the line? We said that the normal direction is selected such that it points towards the origin, which means that the signed dot function should give a positive value if we plug in the origin into this equation. That means ds of 0, L, which can be written like this, should be greater than 0. It should be strictly greater than 0. Why? Because we do not want the line to pass through the origin. We want to have a positive value for this. Okay. Now, what does this give us? P dot n greater than 0. Yes. So this makes sense because, let's say, for example, we are taking our line in the first example. If we select any point like this on the line, P for example, we see that P and N have opposite directions. If P and N have opposite directions, then their dot product will be a negative number. But since we have a negative sign in front of this dot product, the whole expression, that is minus P dotted with N, gives a positive number. Okay? So that's the first step. What is the second step? Let's look at all of the points here. In the first quadrant, we have x consisting of all of these points, x1 and x2 are greater than or equal to 0. So if we form the dot product of x minus p dotted with n, what do we get? X dotted with p minus p dot n. So how can we write this? Now, we know that this expression is 0 by our assumption. By normal vector selection. So in the first quadrant we know that these two values are positive, right? Because in this example, n lies in the first quadrant. In the first quadrant, we know that x1 can be greater than or equal to 0, and x2 can be greater than or equal to 0, which means that this whole expression is greater than or equal to 0, and this one is also greater than or equal to 0. And to any number that is non-negative, we add a strictly positive number. So what will be the whole expression? The whole expression will be greater than 0. So what does this mean? If we take the dot product of x of any point in the first quadrant, consider the signed dot product function of any point, for the given line, it is strictly greater than 0. So there is no way that this function can take the value 0, which means that this line cannot intersect the first quadrant. So what is the condition for this line to intersect anything, any object? We need to have x dot l equals 0. When can we have this? We can have this if ds x l changes sign and x is change continuously. Let's suppose, for example, we have this kind of a line. We have a normal vector like this. And let's consider, for example, a circle. A circle, this circle is intersected by this line. Why? Because some of the points, the circle is a continuous geometric object, as there are no points that are not, that do not belong, there are no points that do not belong to the circle. So we see that all of the points in front, there are some points in front of the line that belong to the circle. These are these points. These are on the positive side. These are on the negative side. And since the circle is a continuous object, or in this case, the ds function assumes the values 0 here. What would happen if we subtracted these 2 points? Let's say, for example, we again have this line, and we again have the circle, but we somehow remove these 2 points from the circle. And all of these points in front of the circle will give a positive function. ds will be positive on this side, ds will be negative on this side. But since these 2 points do not belong to the circle, ds won't be defined for these points. It's never 0. So if we want to change about, if we want to talk about the sign change, then we have to make sure that the set for which we evaluate the sign distance function has to pass through the line in a continuous manner. Okay, that's one important point. So continuity is an important consideration in this example. In this example, as you can see, since we define all of the points in a certain quadrant to be given by simple inequalities, we can guarantee that these will be continuous sets. That is, the set of points in a certain quadrant is continuous, which means that it is at every point that is there are no points in this set which can be excluded in case the line intersects them. There are no such points. So there is always a continuity. So for these quadrants, we can say that if the signed dot product function changes sign, then it should cross the value, should take the value 0. If there is a sign change for this signed dot product function, then we need to have the condition that the signed dot product function should be 0.